Yeah, so I recommend you to read this review article to give you a very good overview of how the QMM approach works, and it's a basic principle for dealing with the covalent systems. And in practice, using the Chemshell software, we recommend to use the so-called additive scheme of the QMM method. That is to calculate the outer part of the system using the classical method, and the inner part, which is typically the active side where the chemical reactions happen, using the high-level QM method. And Chemshell will deal with the interaction between the two regions, and it's the user's responsibility to partition the whole system into QM and MMM. So if there is a cut between the two regions at the covalent bonds, there would be link atoms, which are normally hydrogens, automatically added by Chemshell, and the link atoms will be calculated at the QM, but all the energies and the gradients will be dealt with by Chemshell automatically. So as the user, you don't need to worry about the interaction. This typical method how we deal with covalent systems. For ionic systems, there's there would not be link atom added. So it's the so-called polarized embedding we recommend to use for this system. Typically, it's metal oxides for solid state, of course. So Chemshell has a lot of success stories, and I'll highlight several of them published recently. So we and our collaborators at UCL just published this text paper. In this paper, we started copper exchanged zeolite. So this kind of material can catalyze the selective reduction of nitrous oxides. Nitrous oxides are the main source of air pollution in reality, and this is highly poisonous to the environment. It's a very important question how to eliminate these species from the air, and so Chemshell helped simulate the reaction mechanism on the site of this zeolite material, and it also simulated the effect of a solvent, which is water in this study. And the second case is cerium oxide, but with vacancy of oxide. So this shows special characters. Normally, you can study the properties using classical force field, but it's not accurate enough. So in this study, we used Chemshell software and the QMM method to develop a node-full force field for predicting the properties of this material. And so we use the polarized force field model in this study. It was also published recently. And for biomolecular systems, there was a Nature paper 3 years ago. So this is an important protein that acts as a sodium pump. So, which means the sodium, the kinetides can be transported to go through the membranes with the help of the key amino acids in this protein. And the Chemshell helped to simulate the dynamics procedure of this sodium transporting or pumping. And on the right panel, it's a similar case, but this iodine chloride is also a protein pump. So what's published on Science, and of course you can use the Chemshell to study reaction mechanisms in enzymes. It's a very typical use case of Chemshell software. So for more studies employing Chemshell, we recommend to read this perspective article we just published last week. And it has a brief overview of Chemshell used in different areas, solid state or molecular systems, since 5 or 4 years ago. And would also recommend another article, was 2019, and it also gives you an overview of the applications using Chemshell from 2014 to 2019. I guess you would like to find out the current status of the software. So you can visit our website, chemshell.org. You can join the mailing list, and you can follow our Twitter account. There are 2 versions of Chemshell. One was started 2 decades ago, more than 2 decades, and it was based on the TCL or Keal scripting language. It's a free for academic use, but you need to apply for a license. And we have stopped the development, but we still maintain it, and you can still use it. Specifically on Young, of course. And you can read the original paper about this version, and also another review paper. And recently we started the project to rewrite to the Chemshell in Python language. You know, Python has been the dominant language even in scientific computing. And we have developing the Python-based version for several years. Just still haven't finished. So now the stable version is a beta, but it's an open source and of course free of charge. And we have several projects running to develop it. To the main purpose is to reproduce what TCL Chemshell can do. And of course, there are a lot of new features added to the Python-based version that are not available in the TCL version. And for the Python-based Chemshell, you can read this article. This was the also the article containing the review of applications. So you maybe pass out which, sorry, what's the ring? Okay. Maybe pass out which version of Chemshell you should use for your scientific research. We would recommend you to use the Python-based version, which has a full functionalities for materials science. So we are confident that you can use Python Chemshell for production calculations. It also, just like TCL version, it contains automated workflow for cutting out a finite cluster model. If you like to find out what this model is about, you can refer to the original 2003 paper. So I'm not going to give you details about these theories. And it also contains the new periodic embedding method, so-called QMME for metal. And you can read our latest perspective article about this method. It's a periodic embedding, so it's different from the models I introduced in the previous slide. For biomolecular systems, we still recommend you to use the TCL Chemshell, which has been proved to be stable for years. And because Python Chemshell is still being actively developed for complete functionality for calculating this kind of system. In T-cell Chemshell, it has features we are still trying to introduce to Python Chemshell. Especially, you can do QMMM molecular dynamics, you can calculate free energy. But of course, if you would like to try the new features in Python Chemshell, because it has an automatic user-guided workflow for preparing the system of, for example, a protein. So it's highly automated, and it has a very low barrier for beginners. And we also welcome you to try this version and to give us feedbacks. And if you have existing models created by T-cell Chemshell, you can port it to PyChemshell, and vice versa. You can prepare the solve the model using PyChemshell's workflow, and you can calculate its use T-cell Chemshell. We provide facility tools for doing this. As I said, Chemshell is highly scalable, so you can use the standard MPI parallelism, which will accelerate the calculation, especially on QM calculation, which consumes most of the CPU times. Sorry, please. Can I resume? So I can't go back to Zoom. That's strange. Okay, I'll just show the slides in this way. There's also an advanced type of parallelism available in Chemshell. That's the so-called task farming. In brief, it means you divide the tasks into different work groups, and each work group still contain the MPI parallelism. So there are two hierarchies of parallelism in this type. And it's very useful if you have a combinational task which contains multiple independent single point calculations. And typically you have if you calculate numerical gradients or Hessian, it can be task farmed, or you scan a potential energy surface, or if you optimize the transition state using this non-elastic band map method. We are developing a great feature that can calculate the infrared or Raman spectroscopy using Chemshell at the QMM level. The code will be available soon. It also can utilize the task farming feature to accelerate the calculation. We have provided a range of interfaces to external software programs in Python Chemshell. It contains different choices of QM codes, and for MM we have Keal Poly, which is open source already, and the Gulp, which can calculate molecular systems, of course, but we normally use it for materials science. The NAMD can be used for preparing the solvated systems of biomolecular study. We also provide several interfaces to external plugins like Monte, which can drive Monte Carlo simulations. Field can prepare the force field file for Poly calculations. And we have an interface of the basis set exchange. So you can name a basis set's name, and you can get the files ready for calculation very easily. And PDB to PQI is also used for preparing for solvated model of a protein. And we also have an interface to Atom, which is the molecular visualizer convenient for solid state. So before I go to the technical details for Chemshell on Young, do you have questions so far? Then I'll continue. For accessing Chemshell software on Young, you can load the pre-installed modules for TCL Chemshell. So by just typing the command module load, you'll find two versions installed there. And for using other QM codes like NWChem or Games UK, you need to load the associated modules separately. And for PyChemshell, it's not yet pre-installed as a module on Young, but you can download it from our website. It just needs a simple registration, and you can download the latest release. PyChemshell needs to be compiled yourself on Young, but it's pretty simple. First of all, you need to load the Python module because the installer uses Python language. And then you run the setup script, which is executable using the argument platform Young, which contains the preset for the specifications for compiling on Young. And it will be MPI parallel version. But running this command will only result in standalone Chemshell without any external code. So you need to use the arguments for compiling other things. And Chemshell will do the compilation for most of these codes. So you don't need to pre-compile them. And just to keep in mind that you always need to combine these arguments together. Otherwise, unless you don't want to use an option of them. For example, if you don't want to gulp to be compiled with Chemshell, you need to remove it from your options. Typically, if you want gulp to be compiled with Chemshell, you just give this dash gulp and just to specify a pre-downloaded source folder to gulp. So we support the latest version up to 6.2. But NWChem is because NWChem is open source, it can be downloaded by PyChemshell automatically. And you just need to specify this dash NWChem. You don't need to pre-download it yourself. And the Games UK requires academic license, so it's similar to Gulp. Poly is open source. You only need to dash Poly, and likewise fields, NMD, and other plugins like PDF to PQR. For using the charm force field, it's not the charm program. To download the force field data, you need to specify charm dash ff. For running T-cell Chemshell on Young, you know, the Young system relies on the Q sub, and so you need a script containing the Q sub information. I believe you know this better than me. And the difference is only to load your specific TCL Chemshell module under these specifications. And you also need to load NWChem if you want to use it for calculation QM part. Then you run the Chemsh executable command, which is a script, and the path will be defined by loading this module, of course. And -p in TCL Chemshell means number of MPI processes. So, for example, if you want to use 40 MPI processes for calculation, and you need to specify your input script. I'll show you how TCL Chemshell's input looks like. If the job is task farmed, we need to specify a number of work groups. And the division of the work groups will be done by Chemshell. And you, of course, would like to redirect your output to a log file. Then you run the qsub command to submit your job. For PyChemshell, of course, you can do you can prepare a similar script and use the qsub to submit your job. The difference is that you there's no pre-installed module on Young, so you need to specify the path to your own Chemshell executable. the argument is a bit different from T-cell Chemshell. So minus NP means number of MPI processes, and minus number of work group will define will switch on the task farming. If you don't specify this as a non-task farm job, and the rest is a standard Chemshell command. So I'm going to tell you about this because PyChemshell provides a feature for automatic submission. You just run the script and you specify an argument minus submit, and Chemshell will submit the job onto the young compute nodes automatically. So I've explained how to specify a parallel job, and you need to give a job name, and you need to specify a project code, like and by using your project budget, like free or gold, and then you need your input script. So now I can give you an example how the input scripts look. So let me share my shell. Hope we can see clearly. So now I have a logout node of young, and if I go to the examples folder of the result Chemshell, you see a lot of dot files, which are typical extension for T-cell Chemshell's input, means Chemshell. So I can open the typical one. And T-cell Chemshell, the input script is a T-cell script. So basically, it follows the T-cell syntax, but it supports predefined T-cell Chemshell functions. So if we start from creating a structure, we use this Z matrix creation command. But of course, you can read in XYZ file, for example, PDB file, but you can refer to the menu. And then we can use this command to read input to read in force field definition. And this an optimizer's name. So it means this geometry optimization task. And then we have a few keywords defining the methods or parameters we use. The coupling means the coupling method is shift. In T-cell Chemshell, it specifies the electrostatic embedding, which means the QM part is polarized by the external electric force field provided by the MM environment, but the MM part isn't polarized. Of course, we need to define the QM region by specifying the indices of QM items you want. You need to keep in mind, T-cell, according to the language, it always it counts starting from 1. but in Python, it starts from 0. So it's a big difference. And you can define the atomic charges, and then we need to specify which QM code to use, which code to use, and also their specifications. Like this is a so this command will run the calculation already, and for checking the results, we can print out the resulting energy. And for mechanical embedding, and do this, for example. So the difference, is that the keyword coupling is missing. So mechanical embedding means neither QM nor part is polarized. So find another example for you. Because that was a water diamond, so there's no cut along covalent bonds when we partition the system into QM and parts. In this case, it's a butanol. We use a similar computational specifications, but when we specify the QM region, the system along a covalent bond is divided into 2 parts. But after running it, you find the input files for the QM method, which is Games UK in this case, and you find that hydrogen as link atoms have already been added automatically by Chemshell. So also going to show you the Q sub script. I think you are familiar with this format. So if we go to a Python control folder, you find a folder called the text, which have examples in T-cell control. And you find a few examples from very basic one, like in this fragment folder, you find how to manipulate structure in in Python control. So just similarly, this is a Python script, but enhanced with Chemshell functions. For example, you can create a fragment, and the fragment is a predefined type in Python Chemshell, so we can't change its name, but it's a variable name, benzene. It can be arbitrary. You can call it my benzene. And the clause is the keywords to import external file like this XYZ. It's just a standard XYZ. And by reading in this file, the structure, the geometry information will be loaded into this object. So then you can calculate the Z matrix from the Cartesian coordinates. You can print its coordinates by accessing this coords, and it's prefixed by a dot. This is a typical Python syntax, meaning that the latter part is a member of the previous part. And for Python syntax, you can read articles from the internet or follow some tutorials to learn the basic Python to be very useful. And at last, we can save the structure to a new file. We also use this dot syntax, but save is a inbuilt Chemshell function, and you can specify a new file name. For example, we can calculate the connectivity table of a structure. In this case, we read in a chemical JSON format for a ethane molecule. And after that, the connectivity between the atoms will be calculated automatically by Chemshell. And in this test, in this example, we validate if the connectivity is correct. So for doing calculations, I can start with showing an example of a pure QM calculation. For example, here is a water molecule, and we can create the fragment by reading in this external file, and then we can create an NWChem object by using the predefined class of NWChem. And be careful, Python is case sensitive, so you can't change the case of these letters. But this is arbitrary variable name. There are some important keywords when you create this object. One is frag equals, but it can be the input value can be the object we just created. This is the water in this case. Then we define the method DFT of Hartree fork, and then we define the basis set. SP is means a single point. So in this example, we just calculate its energy, and then you can access the energy value by the variable name dot result dot energy. We remember SP is an arbitrary name, but the remaining part is fixed in Python Chemshell, so you can't change it. And I'll show you a geometry optimization example. For example, this one. The previous part is similar. And we support dispersion correction, like Gamer's D3 model for NWChem's DFT. And in this case, we use this type of a task called OPT, geometry optimization. And then we specify theory, we specify the optimization algorithm and some criteria, and also max cycles of optimization, also max number of single point energy evaluations. The default optimizer in PyChemshell is this one. It's called DL Find. It's an open source. It's an open source library, which is very powerful. It can calculate energy minimum. It can find transition state structure using advanced algorithms like large elastic band. They can find the conical intersection structures. And recently, we are developing the Raman infrared feature in it as well. And don't forget to use this command. Also for single point calculation, you always need to explicitly use .run function. And in Python, with parentheses, a pair of parentheses is a function. And without this, it just defines the task without running it. It's different from TCL Chemshell. For QMM calculation, I'm also to give you an example. Let's go to Inagural gulp. We also use this butanol as an example. So after creating the butanol structure, we define the force field. But of course, the force field can also be imported from an external file rather than just plain text. Here we also need to define an object of an instance or an object of gulp calculation, which will be used later as the MM method. And QMMM is the object for QMMM calculation. Here we put the frag keyword here in QMMM rather than in NWChem or gulp. And then Chemshell will forward this structural information to both of them. Here you can see the great flexibility in Python. So you can use the Python features to define a range of the QM region, anything that's legal in Python. But be careful, range 5 in Python is actually will result a sequence from 0 up to 5 atoms. So, but TCL starts from 1, so you always need to keep this in mind. And we have different keywords in PyChemshell compared to TCL Chemshell. In TCL Chemshell is a shift. In PyChemshell is embedding, but they mean the same thing. And TCL Chemshell uses shift equals coupling equals shift. On in PyChemshell, it's embedding equals electrostatic. So it means electrostatic embedding. And in PyChemshell, you also need to specify coupling method, which has a different meaning in PyChemshell. So covalence will tell Chemshell to add the link atoms for broken covalent bond across the QM and the MM border. But if this is ionic, it won't add the link atoms. In this example, we can calculate a single point by specifying the QMMM object as the theory, and it can, even for single point calculation, we can switch on the gradient evaluation. If we do a jump optimization, it's just similar. but we use OPT instead. So go back to my slide. So I have given you a preview of the input scripts. It's very slow. Yeah, and as I've demonstrated, you can go to the examples subfolder for examples of the T-cell Chemshell, and we also provide a very detailed tutorial for different types of the calculations. Then for T-cell Chemshell, you can go to the subfolder /tutorial samples, and there are also text explaining these samples online. You can find them on our website. So likewise for T-cell Chemshell, for Python Chemshell, you can go to text folder, and this contains the examples I just showed. And likewise, we also have a tutorial for Python Chemshell in the samples. It also contains a basic introduction to Python language. So how to create a list and how to deal with different data types in Python language. It's very useful if you are not familiar with this computational language. There are also detailed explanation for these samples online. You can always visit our website. If you have general questions, of course, we would strongly recommend you to read through the documentation. And it comes with the source package. In Python, so you need to compile it to get a PDF file or HTML file. Instead, you can see the HTML version on our website. We also have an online forum, and you are welcome to discuss issues, raise questions there. If you have advanced technical issues, you can contact me or contact Chemshell, who's a scientist at UCL and familiar with Chemshell calculations on Young. And if issues with the pre-installed T-cell Chemshell module, you should contact the system administrators. So it's the end of my presentation, and I've left some time for questions. So what can I? Yeah, Hafid was asking, is there example? Is these example files are available anywhere? Yes, I think I've answered the question. As I'm aware of the website, my tutorials relevant files related to those tutorials, or maybe I'm not able to access those files. For T-cell Chemshell, you can always apply for an academic license, and it's a free of charge for users based in the UK. So after downloading this source package, you can find the subfolder containing these examples and also the tutorial samples. And for T-cell Chemshell, it's likewise, it's even easier. you don't need to wait until your application is approved. So you can download the source code from the website and you can find these examples. Yes, I'm answering the question about the Python Chemshell. And for let me show my screen of the logon node again. I can't find the window of show session. Strange. Any more questions?
Yeah, so if we have no other questions, I guess we can thank our speaker. Oh, perfect.
Yeah, so but just going to
Missing a grep.
Yeah. Sorry. It's rather slow. Yeah, so right, if it's just a module load, the standalone version without the gulp. Yes. And so we can use them to show see the path to it. And yeah, like we can access these folders you see. So just after loading the pre-installed modules, you can also access the examples there for TCL Chemshell. And if you download the latest release version of Python Chemshell, the examples also come with the source package. So I guess that's
with that link you had there, you'd have to copy it to your own folder, right, to be able to use them, because I guess there's permission issued in the chat.
You mean this location to these files? I think we have permissions.
But for shared, yeah, okay. Oh, fine. Probably good practice to copy anyway, though, just so that you've got your own version of those Python scripts, right? Or
the Python version, yes, because it's not yet pre-installed on Young, so you always need to download it yourself and compile yourself. For example, show you an example of submitting the job. Yeah, it's how you submit a job of Python Chemshell. It's the recommended way, because you can write a Keal sub script. And if I tried, you see, Chemshell will load the prerequisite automatically for you, and I forgot to stay on the waiting list for a while. Sorry, I'm not sharing my screen, I guess. Yeah, but anyway. And yeah, right. Okay, thank you very much.
I can access sample files. Just one more question. Does Chemshell support amber force fields from biomolecules?
Yeah.
Yeah. So does Chemshell have support for amber force fields for biomolecules?
Not yet. Sorry, not yet. We haven't interfaced to Amber, but we do support the importing of the Amber file type. That is the parameter topology. It's called a PRM TOP file to be imported directly to Python Chemshell. But in TCL Chemshell, yes, I think there is a support for Amber.
Okay. So do we have any other questions at all?
Yeah, there's a new question. I can answer the example first. So, does Chemshell support? Oh yes, sorry. Yeah.
Oh yes, we had that one.
It's just read it for me. Yes. Yes.
Okay. Brilliant. So if there's no other questions, we can. We're about right for time. So I can thank our speaker then. Thank you very much. Very interesting.
Yes. Thank you all for attending, and thank you, Ed, for organizing.
Oh, no, thank you. And so the video will be recorded online. So if anyone wants to go back, I mean, you did some very nice kind of overview of the actual file structure. So it might be people can go back and actually want to implement it, and I guess get in touch with you if they have any specific questions. So I'm volunteering you there. But
Yeah.
Amazing. Well, thank you so much.
Yeah, you're welcome to. Well, thanks. Bye.
Right, brilliant. Thanks.